Hello dear students, and you're welcome to our course. Today in this video we are going to speak about fluid mechanics in chemical engineering. So dear students, let's get started. Fluid mechanics isn't just a science, it is the key to unlocking how liquids and gases interact, whether in nature or technology. And today we begin an exciting journey into this dynamic field. We will explore fascinating questions like how do engineers design rockets to reach space? How can we predict the flow of water to prevent floods? Yeah? And let's dive and see where the currents of learning take us. Here we see fundamentals and applications, efficiency, and the CFD forms of fluid mechanics. As for fundamental, it's understanding fluid properties and governing equations is essential. So fluid mechanics is vital for reactor, heat exchanger, and the distillation design. Optimize flow patterns to reduce energy waste and enhance product quality and efficiency, and CFD simulations for detailed analysis and design optimization. So, fluid mechanics is governed by a set of fundamental equations that describe the motion, behavior, and interaction of fluids under various conditions. These equations are rooted in the principles of conservation laws and serve as the foundation for analyzing and solving fluid flow problems. And here you see some key equations, Navier-Stokes equations and the fluid dynamics. These equations describe the motion of fluids by taking into account forces like pressure and the inertia. They help us understand and predict how fluids behave under various conditions. Solving these complex equations often requires computer simulations. As for fluid dynamics, by solving the Navier-Stokes equations, we can model the simulate fluid flow in intricate systems. This enables engineers to optimize designs, predict performance, and troubleshoot potential problems in chemical processes. These equations form the backbone of fluid mechanics, enabling engineers and the scientists to model, analyze, and optimize fluid flow systems in a wide range of applications. Fluid mechanics plays a vital role in a wide range of industries and natural phenomena. Its principles are used to analyze, design, and optimize systems involving fluid flows interactions spanning diverse fields from engineering to medicine and environmental science. So, what about applications of fluid mechanics? Reactor design. Fluid mechanics plays a very important role in design of chemical reactions. Optimizing flow patterns within the reactor ensure efficient mixing of reactants. As for heat exchanger design, efficient heat transfer is vital in many chemical processes. Understanding fluid flow patterns within heat exchangers allows engineers to maximize heat transfer efficiency and minimize energy consumption. Distillation processes. Distillation relies on precise control of fluid flow to separate components based on boiling points. Fluid mechanics is essential for optimizing column design and ensuring efficient separation of components. Fluid flow in chemical processes. Fluid flow is essential for transporting liquids and gases throughout a chemical plant. Pipes, pumps, valves, and other components are critical for efficient and safe transportation of fluids. Mixing of different fluids is often crucial in chemical reactions. Fluid mechanics helps optimize mixing processes to ensure complete homogeneity of reactions, leading to more efficient reactions. Separation process such as distillation, filtration rely on controlling fluid flow to isolate desired components. Fluid mechanics guides the design of efficient separation equipment. Dimensionless numbers play a critical role in fluid mechanics by simplifying the analysis of complex fluid flow phenomena. They allow engineers and scientists to understand, predict, and scale fluid behavior across various systems without relying on specific units. So here you see why dimensionless numbers are so important. For example, many fluid flow equations contain multiple variables with different units, making them complex to analyze. Dimensionless numbers simplify these equations by grouping terms into non-dimensional forms, reducing the number of independent variables. For example, the Navier-Stokes equation can be simplified using dimensionless parameters like the Reynolds numbers. Dimensionless numbers enable the comparison of fluid flows in systems of different sizes, fluid types. For instance, for two systems with the same Reynolds number exhibit similar flow characteristics regardless of their scale. This principle is used extensively in modeling and experiments such as wind tunnel tests. Computational fluid dynamics, CFD, computer simulations. CFD uses sophisticated software to solve the Navier-Stokes equations and simulate fluid behavior. This allows engineers to test different designs and conditions without physical experiments. Visualization. CFD provides detailed visualizations of fluid flow patterns, helping engineers understand complex flow behavior and optimize process design. Dear students, as we come to the end of today's video lesson, let's take a moment to reflect on what we have explored. We dived into the fascinating world of fluid mechanics, a discipline that not only governs the flow of liquids and gases, but also shapes many aspects of our lives, from engineering innovations to understanding natural phenomena. We examined its fundamental equations, the significance of dimensionless numbers, and how these principles are applied across industries and research fields. Thank you for your active participation today, and the next time we are going to speak about heat transfer. So, dear students, thank you for your attention and be ready to discuss next video session.